In this video, we discuss calculating our t-score and p-value in a one-sample t-test. So you've determined that a one-sample t-test is designed to answer your research question, and you know that your data satisfies the key assumptions required to perform the test, and now you have your hypotheses worked out. How do you go about calculating your test statistic and determining your p-value? The formula for a t-test is very straightforward. You calculate a t-statistic, which is equal to x bar minus mu naught divided by the standard error of the mean. Now remember, the standard error of the mean is the standard deviation we would see if we had an infinite number of samples this size, calculated means for each sample, and then calculated the standard deviation of those theoretical means. It's our yardstick for how large of a difference we would expect to see between our sample mean and mu naught. In that way, the one-sample t-test follows the same general classic pattern that we saw with z-scores. How big of a difference did I see divided by how big of a difference did I expect? And remember, the formula for the standard error of the mean is equal to the standard deviation divided by the square root of the sample size, n. Notice that because we don't know the population standard deviation sigma, we use the sample standard deviation s instead as our estimate of sigma. And remember, it's the lowercase s with n minus 1 in the denominator. But otherwise, the standard error is exactly the same as when we were doing it with sigma, and we interpret it exactly the same way. Now, looking at the formula for our t-statistic, it should also be evident that the t-score, just like the z-score, can range all the way from negative infinity to positive infinity. Now with the z-test, the z-scores follow the normal distribution, but t-scores follow what's, surprise, surprise, called the student's t or just the t-distribution. It's a lot like the normal curve, but a little different. Let's take a look. Okay, here's a normal curve. As we know, it's symmetric and unimodal, meaning the mean, median, and mode are all the same. Now let's draw a t-distribution on top of this. The t-distribution looks a lot like a normal curve. It's also symmetric and unimodal, except it's a little flatter in the middle and a little thicker in the tails. Now think about what that means. No pun intended. It means that we're more likely to get larger t-scores than z-scores because there's more cases out here in the tails. Now, the big difference between the t-distribution and the normal curve is that the normal curve is the normal curve is the normal curve. It's always the exact same shape. The x-axis may change depending on what we're actually looking at, but that shape of the normal curve is always the same. In contrast, the exact shape of the t-distribution changes based on what are called the degrees of freedom. The degrees of freedom are related to the sample size and some other things. It's a consequence of the fact that we're estimating sigma instead of knowing the population standard deviation. Now, if you're interested, I have another video that talks more about this, or you can take it on faith. For the one-sample t-test, the degrees of freedom is equal to the sample size n minus 1. Before moving forward, let's take a quick look at the shape of the t-distribution and how it changes based on the sample size and the degrees of freedom. So here's the t-distribution when our sample size is 3, which means our degrees of freedom is equal to 3 minus 1, or 2. And here's the t-distribution when our sample size is 6, meaning the degrees of freedom is 5. Notice it's a little closer to looking like the normal curve. And here it is when n is 10 and the degrees of freedom are 9. And here the degrees of freedom are equal to 19. And the degrees of freedom are equal to 29. In fact, as n approaches infinity, and as our degrees of freedom approach infinity, the t-distribution more and more closely approximates the normal curve. So the t-distribution looks a little different from the normal curve, but other than that, we use it in exactly the same way. Now, we do always need to note the degrees of freedom because we need to know exactly which t-distribution we're talking about. We need to know exactly what the shape is, how flat it is in the middle, how much more inflated it is in the tails. But then we simply estimate how extreme our t-score is, just like when we estimated how extreme our z-score was with the z-test using the normal curve. Okay, let's continue with our example. We were looking at babies whose mothers had no health insurance, and we'll use the standard alpha of 0.05, meaning that I only want to make a type 1 error, rejecting the null when it's true, 5% of the time. I also know that mu naught, the population mean if the null hypothesis is true, that value I expect to see on average if there's no difference, is 3,400 grams. I want to specifically test whether babies whose mothers had no health insurance had lower birth weights, so my alternative hypothesis would be mu1 is less than 3,400 grams. Across the population, I think that the mean birth weight for babies whose mothers do not have health insurance is less than 3,400 grams. And my null hypothesis would be mu1 is equal to or greater than 3,400 grams. In English, my null hypothesis is that babies whose mothers had no health insurance have a birth weight equal to or greater than 3,400 grams. So I go out and sample 25 babies whose mothers did not have health insurance, and their mean birth weight was 3,200 grams. Remember, we don't know the population standard deviation. That's why we're doing the one sample t-test instead of a one sample z-test. But I do have the sample standard deviation, which we'll say was equal to 600 grams. Based on this information, our standard error is equal to 600 divided by the square root of 25, or 600 divided by 5, or 120. The t-score is then equal to 3,200 minus 3,400 divided by 120, or negative 200 divided by 120, or negative 1.67. The mathematical notation for a t-statistic is written as t with 24 degrees of freedom is equal to negative 1.67. Remember, the shape of the t-distribution varies based on the degrees of freedom, so it's important to report the degrees of freedom in parentheses after the t. You don't want to simply report t equals. You need to report t with 24 degrees of freedom equals whatever. It may seem a little picky, but report your t-score correctly. An italicized t followed by the degrees of freedom in parentheses. Don't get lazy or sloppy or report it some other way. Now, to see how we go from our t-score to a p-value, it may help to visualize things. Again, mu naught was equal to 3,400, and this is the population mean to which we want to compare babies whose mothers had no health insurance. If the population mean for those babies really was 3,400 grams, and we collected an infinite number of samples, The standard error of 120 tells us that the standard deviation of those means would be about 120 grams. This is our yardstick to measure how large of an effect we actually obtained. Again, if the null hypothesis is true. From that, we can create this distribution for the means that we would expect to see if the null hypothesis were true. Now remember, this is a theoretical distribution of means that we would expect to see if the null were true. Finally, let's also add in the t-scores for these theoretical means based on the standard error of 120. Our sample mean was 3200, which we just determined is equal to a t-score of negative 1.67. Okay, is that a big deal or not? It's kind of out there in the tail, but is it extreme enough? Well, that's what the p-value tells us. Remember, the p-value is the probability of obtaining a result as extreme or more extreme than what was observed in the direction of the alternative hypothesis if the null hypothesis were true. So we have a t-score of negative 1.67, and our alternative hypothesis is that the average is less than 3,400. We'll reject the null with low negative scores, low negative t-scores. So the p-value is the probability of getting a t-score of negative 1.67 or more extreme in the lower tail. It's equal to the blue shaded area here. Based on the t-distribution, we can easily check and find that the area below a t-score of negative 1.67 is equal to 0.054 or 5.4%. Our p-value is therefore equal to 0.054. In other words, if the null hypothesis were true and the population average for babies whose mothers had no insurance really is 3,400 grams, with a sample of 25 babies, 5.4% of the time, we would have randomly ended up with a mean in our sample of 3,200 grams or less. We then compare our p-value to our alpha level, which was 0.05. Remember, the alpha level tells us how small our p-value has to be in order to reject the null hypothesis. It's how unlikely the result has to be in order to say, look, that is so unlikely if the null hypothesis is true that I'm comfortable concluding the null probably isn't true. Let's reject the null hypothesis. Now, in this case, the p-value indicates that if the null hypothesis is true, 5.4% of the time we would have obtained a mean this extreme or more extreme in the direction of our alternative hypothesis. Again, if the null is true. Now, our alpha was 0.05 and our p-value is 0.054, so it's close but not quite small enough. It has to be less than 5% of the time in order to reject the null. So we failed to reject the null hypothesis. Now, just like with our one sample z-test, there's a second way that we can approach this and come to our conclusion using critical scores and our region of rejection. Okay? To start, let's go back to the distribution of means that we would expect to see if the null hypothesis were true. Because we had a directional hypothesis that the mean for babies whose mothers had no insurance is less than 3,400 grams, we're only interested in rejecting the null when our sample mean is in the left-hand tail. But how extreme does it need to be? Where's that line in the sand? What's the point at which only 5% of the hypothetical means are as extreme or more extreme if the null is true? Now remember, with t-scores, the shape of the distribution, how thick those tails are, depends on the degrees of freedom. In this example, our sample size is 25, So with n minus 1, we have 24 degrees of freedom. Because we have a directional test in that lower tail, we need to find the critical t-score, that value of t below which 5% of the scores fall. Now, we can do that using tables or Excel or even many calculators now. But in this case, with an alpha of 0.05 and 24 degrees of freedom, our critical t-score for a one-tailed, lower-tailed test is negative 1.71. Whatever mean or standard deviation we see in the raw scores, we know that 5% of the distribution falls below a t-score of negative 1.71. So our line in the sand, that score we need in order to reject the null hypothesis, is a t-score of negative 1.71. We call this our critical value of t because we need to exceed it in order to reject the null. If the null is true, a sample with a mean below a t-score of negative 1.71 would happen less than 5% of the time. That's sufficiently unlikely that one would conclude that the actual population average can't, well, or more accurately, is extremely unlikely to be equal to 3,400 grams. So we reject the null. Because we reject the null hypothesis for scores in this range, we call it our region of rejection. Now, it may help to see what's going on if we convert the critical t-score back to the original units in our study, which were grams. So in this case, let's calculate what the critical score is in terms of grams. In other words, what's that weight that our sample mean needs to be lower than in order to reject the null? The formula to do this is pretty straightforward. The critical score in our original units, not t-scores, is simply mu naught, the expected mean if the null hypothesis is true, plus the product of the critical value of the t-score, the t-score we need to obtain in order to reject the null hypothesis, times the standard error of the mean. Plugging in our values, we have the critical score is equal to 3,400 plus negative 1.71 times 120, or 3,194.8 grams. A t-score of negative 1.71 is equal to a mean birth weight of 3,194.8 grams, using these rounded values. They're the same thing, just one is measured in standard errors or standard deviations of means, and the other's measured in grams. Again, this is the distribution of means that we would expect to see if the null hypothesis were true. If the mean for babies whose mothers had no insurance is equal to 3,400 grams. Given that, we just determined that our critical value, our line in the sand, is a mean birth weight of 3,194.8 grams. A sample of 25 babies needs to have an average that's less than 3,194.8 grams in order to reject the null. So, how did our sample do? Remember, the mean for our sample, x bar, was 3,200 grams. Just a little bit too large. It doesn't quite cross our critical value. It's not in the region of rejection. So we must fail to reject the null hypothesis. Again, we get the same conclusion whether we see if the sample mean falls inside the region of rejection or whether we calculate the t-score and the p-value. Now, in practice, you can see that using the t-score and p-value can be more straightforward and direct. Plus, it gives you the p-value, that probability of obtaining a result that extreme or more extreme, not just whether you reject or fail to reject the null. So you may ask, why even mess calculating regions of rejection and critical scores? Well, We'll see later that this information can in fact be very useful in other ways, such as determining what's called the power of a research design. Plus, it's just good to understand what's going on in hypothesis testing from both of these perspectives so that you're not just simply plugging and chugging numbers into equations. So, wrapping up our summary of the problem, we can now add that our t-score, our test statistic, was a t equal to negative 1.67. Notice that we included the degrees of freedom in parentheses after the t. This corresponds to a p-value of 0.054, which was greater than our alpha level, so we failed to reject the null hypothesis. We conclude that the mean birth weight for babies whose mothers had no insurance is equal to or greater than 3,400 grams. That wraps up this video. In our next video, we'll go through a two-tailed example before we examine confidence intervals for our estimate in the final video that's part of this series. Okay? Bye for now.